Okay, so I'm going to give a characterization of cofibrations now. Of cofs. Okay, so maybe I'll chop the page here. And so the theorem is the following. So the theorem is the following. Maybe I should draw. Let me just say it first. Okay, so let me draw the mapping cylinder. Okay, so we saw before, right, that all cofibrations are closed. So let's let f from a to x be a closed immersion. Okay, this means that that A is isomorphic to its image as a topological space, right? And that the image is a closed subspace of X. And so we can really identify A with a closed subspace of X. Okay, so the following is equivalent. So a character. So you can have a cofibration, or right, and I'll draw the mapping cylinder in a certain way. So the mapping cylinder can be drawn like this. So well, let's see. So we have. Let's draw it like. Okay, let me just draw it like this. Okay, so we have X cross I here. And what we want is we want this thing to retract onto this piece here. So okay, so this piece down here is X cross 0. So we're doing 0 down here and 1 down here, 0 down here and 1 down here. And so this is A cross I, right? This little block here. This is A cross I, right? And so what we want is we want this thing to retract onto this piece here, okay? So okay, so what do I want to say, okay? So and what does this thing look like? So this thing is actually, if we were going to write it down, it looks like A cross I union X cross 0. So the statement that I want to make is that the theorem is the following theorem. Right, so the following are equivalent for F as above. What? One is that F is a cofibration. 2 is that X cross A deformation retracts onto this. Onto A cross I union X cross 0. And then 3 is that X cross I, it just retracts onto A cross I union X cross 0. Okay, so this is the example of what we have here. And so maybe something to observe here is that this thing is really the mapping cylinder as well, right? So notice that, so note that in this situation, A cross I union X cross 0 is really the same thing as this mapping cylinder. So we just have drawn it in a different way, you know. Another way to draw it we could have done this. Right, and then this thing here is A cross I, and then this part here is X cross 0. But I guess at 0, the difference is in this drawing here is, you know, the 0 part is identified with the image, not the F part, not the 1 part, right? So it's kind of just oriented in oriented in an opposite way. Okay. All right, so maybe it's good to give an example before going into the proof of this, right? So what do we think about? So here's an example of how you can apply it. right? So we're going to use this criteria to show something. So if we look at this disk here, so this is this filled disk, and so this is going to be X. And then we have the boundary here. So that's just this circle, and this is A, right? So then we have X cross I. So that's this thing. So that's this filled cylinder. So it's filled, right? And then here, so we need this to be a deformation retract, right? So we're going to have it like this. This thing, the bottom part's filled, but this is hollow now. So it's like you can take your solid cylinder and just kind of like cave it in. Okay, so this is a cofibration, right? So A into X is a cofibration. Right? Because this is our X cross I. This is X cross I. And this is A cross I union X cross 0. Okay, so we just have the bottom part here. All right, so this is our characterization. So let's do the proof. Okay, so as we saw previously, right, the homotopy extension property, right, can be formulated via another diagram. So the homotopy extension property, right, we have this diagram here, I cross 0, I0, I0, A cross I, X cross I. So this is how Catherine Hess writes it, and I kind of like it. So if we have a homotopy here, and we have this one here, like this, then we get this map here. Right? So for every H and seed, we get this homotopy extension. Okay? And so what we'll do is we take Z to be A cross I union X cross 0. So we'll take it to be this boundary piece. Okay? This bottom includes into it as the identity, right? So H is, well, and H0 tilde. Okay, so this is the bottom piece. So this is the identity on X cross 0, right? This thing here is going to be the identity on A cross I, right? So this thing just includes inside this space, like so. So this is the mapping cylinder, right? And so by the homotopy lifting property, right? So by the homotopy extension property, right? Once we do these, we get some H tilde, right? And so H tilde, what is H tilde? H tilde is a map from this thing into here, into, and so let's write out what this is. A cross I union X cross 0. All right? And so now, this proves that 1 implies 2. So this proves 1 gives 2. That is that that being a cofibration gives you the deformation retract. Okay. All right. So conversely, right, every homotopy extension factors through the mapping cylinder. So I said that this was the mapping cylinder. So conversely, so this is saying, so every homotopy extension. So again, this thing here is factors through MF. Okay, so let me say that if you have this, so let's draw this out, right? So okay, so given, so we're going to use the universal property here. So given So one of these setups like this. So A cross 0, A cross I, X cross 0, X cross I, and then we have Z now. Now, some genuinely mysterious Z, okay? H0 tilde, okay? And this goes into here. This is just our we called this F, I guess, not I. I might have called that I on the previous page. I think we're okay. Oh, I did call it I. Oh well. Yeah. This was F. This is what we called F. Oh, yeah, that's what we called F, and this is still the inclusion at 0. Okay. So this is, okay, so we have these, so given a diagram like this, so this is the inclusion into 0. So we get this H tilde. So that's what this is what this map would say. So it would say that, so this is what we want to show, that we have one of these, okay? So, but what we're only given is this in the case of the mapping cylinder, okay? So, but what we do have is so if you look at this diagram, so this is, if you look at this push-out diagram, we do get a map to the mapping cylinder. So by universality, right? So we get some map for the mapping cylinder to Z. Okay, so so this thing here is really the push-out diagram here. Okay, so okay, so what do I want to say about this? Okay, so what I want to say is now we're gonna fit this into a diagram. So this is by this being the initial object in this diagram. So we'll get maps from here. I can't really draw it so well, but here to MF, and those factor through this thing. So the maps here to Z factor through the mapping cylinder. Okay, and so now we can set up a diagram as follows. Okay, so now I'm going to set it up like we have before. So now we have the homotopy lifting property. So we have our initial homotopy. We have our base map here. This was the map F. Okay, this includes into the bottom of the mapping cylinder again. Right. So here's the bottom. Right, and then here's A cross I. Okay, and so we have this universal map U that gives us this map here, and then what we can do is we can take this universal map and raise it to the I, and so that's just the paths like so. That gives a map here Z to the I, and this is also this map's evaluation at 0 and this map's evaluation at 0. So okay, so what I'm saying is that if you have the homotopy extension property for the mapping cylinder, then you get the homotopy extension property no matter what. Okay, so so the homotopy extension property. So look, it fits into the diagram. So now we have a map. So by composition, we get a lifted map like so. Okay, so the homotopy extension property for MF implies homotopy extension property in general, right? And that's what, and I claim that that the homotopy extension property for MF is precisely this statement here, right? That that we have that we have these maps here. So I had to take a mulligan earlier. Okay. I do not want to stop recording. Okay. All right. So that's that. So this proves 1 and 2 are equivalent. Okay. Next, what do we have? So now we need to deal with 3, which is that deformation retracts and retracts are the same thing. Okay. So clearly, a deformation retract. 2 implies 3. So a deformation retract gives you a retract. Okay. So, but now we need to show that 3 implies 1, and that implies that comes from a trick. Okay. So to show 3 implies 2. Okay, so the idea is to do the retract slowly. Okay, so suppose what we do is we suppose that we have just a retract, not a deformation retract, x cross I, into this mapping cylinder, but kind of flipped with the 0 and 1. Okay. All right. So sorry if I'm not being consistent here. This is the same thing as x cross 0. I've been writing it like this over here. Okay. And so let's write it out in coordinates. So in coordinates, all right. So we'll write r of xt, and it's going to have 2 components. And so we'll write it as alpha of xt. So this is the part that goes to a and tau of xt. All right. So there's these 2 parts. Okay. So what we'll do is, and so there's some conditions, right? So the condition is that unless tau of xt is equal to 0, right? So that means that unless it's in the boundary, right? So unless it's in this part here. So let me draw the drawing again. So a cross I, x cross 0 is this part here. Right, so here's 0 and here's 1. So unless it's in the boundary, right? Well, what we need to have is we need alpha to be in alpha of xt is an element of A. Okay, and so so other properties that we have, right? Right. So we'll have that, alpha of AT. This is A, so it retracts onto it, and alpha of so in tau of AT, so that's the time is t, and then alpha of, so this is one property that we have, and another property that we have is that on the other boundary, on the other component, right? This is fixed. Okay, so it says that this is saying that the retract is fixed on the mapping cylinder. Okay, and so the trick is this following homotopy. So what we'll define is h of xt s, and so this needs to be, we'll do it like so. So s is in between 0 and 1, and we need it to be the identity starting at 0, right? So we have alpha of x ts like this. So when s is 0, that this thing just becomes x. And then what we'll do is we'll take a straight, so then we'll do t1 minus s plus s tau of xt. So we do a straight line homotopy between t and tau of xt. Okay? And so you can do is so this is the trick, and so you check that this is this gives the deformation retract. Namely that h of xt at 0 So this is the identity on x cross I. And h of xt of 1, so this is the retract that we constructed. Okay? And so that proves that those three properties are equivalent. All right. So I'm going to pause here. There's a third thing which is called neighborhood deformation retracts, which I'll say a little bit about right now.